Okay guys, welcome back. I couldn't believe it. So quiet here, right? Compared to what we have in the class. Anyway, at the beginning of the semester, okay, if you still remember, I introduced you to the different techniques in order to achieve, the data anonymization and differential privacy, right? And if you still remember the technique that we use, can observe there is a similarity between all these techniques, okay? Let me show you what do I mean with that. Okay, so when you work with the differential privacy and the data anonymization techniques, we start with the actual data here, right? Then what we did here, we convert this data into what? To another data, right? Either we're gonna suppress, for example, say S, or generalization, right? Techniques, okay? Or we can use, for example, differential privacy in order to add the noise here. So what's gonna happen to the accuracy of the data? Accuracy of the data can be changed, right? We're gonna lose some accuracy of the data. Good. Last lecture, we started focusing on with the different techniques, right? So the data wouldn't change. Actually, when you say the data can be changed, actually the data can be changed somehow, right? But the accuracy can be the same. Because with the crypto, we're gonna take the actual data, then in order to perform the same encryption, this data using, say, a key or whatever, then you're going to produce the ciphertext. Okay? You can perform some computation of the ciphertext, but once you decrypt it, you're going to get, the accurate data back. Okay? So that means in this case, the accuracy will be high. Okay? Wouldn't be dropped. So we still have 100% accuracy here after before our computation of the data. Okay? Good. So last week we went over a quick overview about crypto in general. Starting this lecture, we're gonna be more specialized or specific. Okay, so we're gonna start looking at the first topic here. We're gonna look at secure multi-party computation. Okay, we're gonna start first with the definition. Okay, and mainly the secure multi-party computation, which is gonna be the most important, say, building block that we're gonna use in many privacy preserving algorithms. Okay, so we're gonna have a different techniques. Again, we are not gonna work with, say, with the anonymization, suppression, generalization, differential privacy. No, we're gonna talk about the crypto to perform or achieve the privacy preserving. Okay, so secure multi-party computation is involved in, say, security and the privacy. If you look at the data that we work with before, the differential privacy, we mainly have what? We focus on the privacy, right? So we need to protect, for example, if any user is inside the data or not, whether we need to generalize, for example, the data to another format, for example, so the tracker cannot, identify the users, right? So we still talk about the privacy. That's what we talked about before. But now, today's lecture, when we start looking at the secure multi-party computation, we're going to see that we care about the privacy and also the security. Okay? So first, I'm going to give you an introduction for the secure multi-party computations. First, we'll start with the motivation. Okay, what's the motivate us to use the secure multi-party computation in practice? You're going to see there are, let's say, many applications related to the secure multi-party computation in the real world. We're going to look at, for example, what the actual security definition here, what the security guarantee, what the privacy guarantee in general. We're going to see what is, the purpose of using secure multi-party computations. How can you perform that? How can you achieve that? Of the mouse moving very fast. Okay. Then we looked at, see some examples, say some practical tools using the secure multi-party computation. Okay, good. So first let's start, define what do you mean by the secure multi-party computation. In today's data-driven world, okay, collaboration is the key, right? But the problem here, what's going to happen when, for example, that collaboration involves, say, sensitive information. So someone's going to start thinking about, okay, I do have a sensitive information, but we need to collaborate somehow to compute, let's say, specific method or function. Okay, so secure multi-party computation here is defined as a cryptographic technique, okay, which allow multiple parties, okay, to jointly compute a function on their private input without revealing those input to each other. So that's interesting, right? You think about the situation that we have multiple people who wanted to collaborate together, and we can't compute, let's say, a specific function. It might be predefined function or whatever function that we have based on our private input without revealing our private input to other parties. Oh, or the other people that participate in this, let's say, computation. Okay? So we're gonna start, as I mentioned here, provide you the high-level overview multi-party computation or secure multi-party computations. Sometimes you're gonna say MPC, sometimes SMC, either is fine. Okay. We're gonna, as I mentioned, we're exploring its core concepts and applications in general. Okay, good. So this is the formal definitions here. It's the most important thing for the secure multi-party computation is going to allow us, multiple parties in order to collaborate without revealing sensitive information to each other. And it's the most important thing. Okay? So when you talk about the secure multi-party computation, we need to achieve some, let's say, requirement, as we're going to see. Right now, it looks like we need to keep our private information, let's say, protected. Good. So let's start with the first problem here. We're going to talk about the love game, which also known as, you say, the end game. Assume that we have two people. They want to see whether they're going to love each other without revealing their, say, actual feeling. Okay? This is the most important thing here. So, in this case, the input is going to have either going to be 0 or 1. Okay? Assume that we have Alice and Bob, and the input might be 1 and 0, 1 and 0, and you have like a function between them. And the function can be, say, whatever the input of A and the input would be, all right? And the result can be either 1 or 0, okay? The most important thing when you think about the secure multi-party computation here, we need to make sure that this private input, the input of this data, or the, let's say, from the participating in this computation, should be private. No one knows what the actual input here. The result, that's fine. It can be revealed the outcome, all right? That's, the secure multi-party computation. We mainly focus in the computation here. But here we don't care about the result here. Of course, we care. We look for the accurate result. But here, if we infer anything based on this result, it can be protected by other, to say, mechanisms. Okay? So the most important thing we care here about, to say, the procedure, the computation, the process, okay? That's gonna happen here based on the input that you got from different parties. Okay? Good. So that's fine. If you got the output gonna be 0, that means they love you as a friend, right? That's fine. Okay. So the question is, how can we achieve a question, okay, without revealing, the inputs of the participant parties? So in this case, secure multi-party competition works fine. Okay. Good. We're gonna see how can you do that, but at least we need to see the motivation, some examples with the secure multi-party competition. So it looks like we need to compute a function, and the function can be end. Okay. What else? Assume that we have one interesting problem. It's called the Yao Millionaire problem. This problem is the first version of why we need secure multi-party computation. We start people think about the secure multi-party computation. They try to come up with the motivation why we need to compute this one. Okay? So in this case, assume that two children, okay? Pearl, for example, wants to know whether she has more choice than Gersh, and Gersh is going to say, why is she care? I don't want to give you the actual number of toys that I have, but fine with knowing that who has more toys. Okay? We have two people, two children, want to see who's have more toys. Both of them are fine to reveal the result that who's have more toys, but both of them want to preserve their privacy or make sure that their input should be private. Okay? So back to the same problem that we talk about here. It looks like we have, in this case, if you take a look here, we can use the same structure here that we have. We have Alice and Bob, or we have two users or two children. The difference here, for example, each of them gonna have the input, the number of toys here, and the number of toys. Okay, this one should be protected. No, for example, in this case, B doesn't know any information about the number of toys of Alice or A, or say Pearl or Gersh. Okay, and here we do have a function. And what kind of function here? It's not AND. Here we have AND function. Here we have maybe the big comparison, right? We need to compare, for example, whether A greater than B. the number of choice in A greater than the number of choice in B. All right, and this is, I mean, another function. So it looks like we still have the situation that we need to compute like a function, or let's say secure function, based on the private input. Okay. By the way, right now we talk about the simple version of the secure multi-party computations, where we have only two parts that we wanted to communicate. Okay. We can generalize this one if you have more than two parts. Okay. Good. And again, how can you get this information or give this information to the girl without, I mean, let's say revealing anything else except the result, the number? Who's get? I'm sorry, not the number. Who's get? I mean, the more choice. Okay, good. So we define something here as a secure function evaluation. That's what we're doing so far. It might be and, it might be simple function, it might be, I'm not going to say complicated comparison, or maybe you're going to have more advanced function. Okay, as we're going to see in the data mining task, yes, it can be one part of the secure multi-party computations. Okay, so here we have, we define this one, the secure function evaluation, and maybe someone is going to say, okay, what's the relation between the secure function evaluation and secure multi-party computation? Again, when you talk about the secure multi-party computation, either you're going to use MPC or SMC. Okay, either is fine. Okay, so both of them, they try to achieve the same goal from the high level. Okay, enable multiple parties with multiple users, multiple people, or many people who wanted to jointly compute, let's say, a function, whatever the function that we have, based on their input. Okay, of their say we emphasize the input should be a private input without revealing, I mean, those input to each other. Good. The terminology can be used interchangeably. Okay, but I believe, oh, actually there is, to say, a difference actually between the secure function evaluation and secure multi-party computations. You can think about the secure function evaluation as like a subset of secure multi-party computations. Okay. Is a specific type, a subset of secure multi-party computations, where the secure multi-party computations is, say, the broader term that encompasses, you say, different techniques in order to achieve, remember, privacy-preserving, okay, computation among multiple parties. And here we're going to achieve the privacy, and also we're going to achieve, I mean, the security at the same time. It's not the same thing that we used to do when you work with the differential privacy. Okay, good. Again, just to make sure that secure function evaluation is like a specific type of secure multi-party computations, with focusing on, let's say, evaluating a predefined method. Let's say less than, greater, comparison, equal, and whatever. Okay, good. Let's have another parallel. Let's go, let's say, a complex example, okay, in order to understand the secure multi-party computations. We're going to talk about the private set, I mean, intersection here. And in this case, we're going to have what? We have, let's say, intelligence, let's say, agency. Each of them, let's say, have a list of potential terrorists, and you need to make sure that to find out the intersection, okay, between these lists in order to identify, let's say, the short threat. Let's do a different example, okay? And that's easy example. Okay, assume that we have three people. Assume that we have, let's say, three people, or let's say two people, or three people, A, B, C, okay? Each of them has, let's say, a list of friends, okay? They don't want to share the actual list of friends that we have, but they try to find the common friends among them. You got this one? Yeah, they don't want to share the actual list of friends they have, each of them, right? But at the same time, try to, I mean, to reveal that the common set of friends among them. For example, they have Alice, Bob, and all of them has Alice, Bob, and here, for example, Alice, and they have different people. So in this case, the common set might be only Alice, right? Which is going to be the part of the result. How can you do this one using the secure multi-party computation? And the same thing here. We have multiple users, A, B, C, whatever, and the result here, we're going to perform intersect, right? We're going to perform A, intersect B, intersect with C. When you say A, B, C, I'm talking about the actual list that each party has, okay? And here the result can be what? can be revealed or shared with every single user. Okay, good. How can you achieve this one using secure multi-party computation? We call this a problem as a private set intersection. Okay, which we define as similar to what we did here with the secure function evaluation. Okay, it would be a specific set of, say, techniques under the secure multi-party computation, if you think this one is high level. Okay, it's a cryptographic protocol used in order to compute the intersection of two sets or more, okay, while preserving the privacy of each set. Okay, good. So when you talk about the secure multi-party computation, hopefully now we understand why we need, or why there is a need to have a secure multi-party computation. This is the situation that we have, and we try to solve using the secure multi-party computation. We have multiple people, let's say multiple entities, each gonna have, let's say, private information, and try to perform a computation securely based on the private input without, revealing this information to anyone. Okay, participate in this computation. Okay, so when you talk about the secure multi-party computation, usually we have like a set of people or parties, okay, or with a private input, and they're willing to what? Try to jointly, right, together, compute the function, okay, of their input. It might be whatever the function. Here, we just to simplify the process, can be the function, it might be any computation task, okay, of their input while preserving, the certain security properties. They try to achieve or ensure two properties. Mainly, it's not two, actually more, but just we look at two, property. The first one, we call this one the privacy. We define this one ensuring that no party learn anything beyond what that can be inferred from the output. Okay. Privacy means in this case ensuring that no party learns anything beyond what they can infer from the output. Okay. Whatever information that you can infer from the output, that's fine. But this is the only thing that you can get, the result and whatever you can infer from the output. Nothing else. Okay? In other words, we can say no sharing of private info in this case. Correctness, that means in this case ensuring that the computed result is accurate. So what does that mean in this case? So let me, in this case, assume that we have, let's say, the first one we said the privacy. That this, the requirement of the secure multi-party computation. That means to say no sharing, let's say, as we said, sharing private info. And the second, let's say, requirement, we said correctness. So in this case, we said the result should be, to say, the same as if we collect, the data together and perform, let's say, the computation. So the correctness means the result should be accurate. So you can simulate back to the list of the friends here. The result should give us this list of the common friends, okay, among all the participating entities here. Okay, assume there's a situation that maybe each of them is going to share their information, or maybe they have trusted third party, for example. They send their information there, trusted third party going to return, let's say, the list of the intersection between every single entity here, all right? So the result should be accurate, should be 100% accurate. Okay, so the functions here, it might be what? Anything, right? We start with a simple function with AND, with the comparison, and it might be, for example, perform a recommendation system, right? Or function, right? That's a different story. So those properties should be ensured even if some of the parties or entities maliciously, let's say, attack the protocol, as we're going to see or talk about the threat model later. Okay? We do have many examples of the application of the secure multi-party computations. Okay, secure election, auction, privacy-preserving data mining, distributed data, and more. Let's take a look at some of them and see how it works in this case. Okay, so in this example here, we're going to look at the application of the privacy-preserving in general. So again, keep in your mind when you talk about the situation that we have, the entities do not trust each other. When they say do not trust each other. They don't share their private information with anyone. So when we can say how, we're gonna see. Okay. The secure election. So assume that we have n parties, okay, or entities or people. They each gonna have what? Gonna have either yes or no. This is my input to the vote as a vote. And the goal here, we need to determine whether the majority voted yes or maybe voted no. It depends what you're looking for, okay? But no voter should learn how other people voted. This is the most important thing. So it means no one knows, my, let's say, private information or my actual vote when I participate in this computation. Auction is another example, okay? So here we have a bidder, okay, and makes an offer. And here, there's the goal here. We need to determine, just for example, okay, who's offered the one without revealing the losing offers, okay. And even sometimes it depends on the application that we have. We are not gonna reveal, let's say, the clear price. And this is one interesting, right? Which makes sense in this case. Actually, that's what you try to achieve, right? Because if I'm gonna reveal, let's say, the one offer or bidder in this case, and reveal, let's say, the actual clear price. So that means in this case, we reveal, let's say, the actual, let's say, value, right, of the actual private data for that entity. Okay. So anyway, so in this case, we're gonna do what? We're gonna reveal, let's say, one without revealing anything else. For example, we have 3 people participate in this auction, and you're gonna say the highest auction or value goes to Alice. I'm not gonna reveal anything else. Here we have another requirement. We need to make sure, besides, the privacy, the data, etc. We need to have what? We have like when you cannot change, your offer later, right? Yeah, when you commit this one, that's done, right? So you send your data, that's your offer. You cannot say, "Oh, I changed my mind." That's a different story. Okay. We have other examples for the secure multi-party computations. This example about the distributed data mining. For example, we have 2 or more companies wanted to compare. This is similar to what we did. Let's say common list of friends. Okay. So in this case, these companies try to what? Try to compare the data sets without revealing them. That's one interesting thing. Okay. We need to build, say, a recommendation system, for example, and we're gonna see, for example, the intersection of 2 lists or more of names for the purchase habits and whatever. Then we need to conclude something. What do you see? Reveal, say, the common or intersection or whatever. Okay. Data privacy, which is one interesting part that I like at most. Okay. Sometimes you're going to try to evaluate this query the data without revealing, let's say, the query to the database owner, or maybe evaluate statistical query in the database. So we do have many, variation. As long as you are not gonna revealing, let's say, the input, you are not revealing, let's say, the value of individual entries, and etc. Let me give you another example about the database privacy here. Assume this is the data owner, okay, and this is the data, my data, okay. Then I wanted to outsource my data in the cloud, okay. I need to make sure that the data should be kept private. So in this case, you're not gonna outsource this one as a plain text. No way. You're gonna do what? You take your data, you encrypt it. I know whatever encryption scheme you're gonna use. Then here we're gonna outsource the encrypted data to the cloud. And the goal here, you need to make sure the data is still usable, right? So you need to make sure that if we have another users, let's say users, allowed to access the data to send a query and get the result, all right? Okay. The problem here, as we're gonna see here, the data can be encrypted. So you need to make sure that how they can be work, or perform the computation, perform whatever query, or let's say encrypted data without decrypting the data, or to try to hide, let's say, even what kind of query can be sent to the cloud. And sometimes you need to hide, for example, the access pattern of the data. I don't want to, for example, to let the cloud notes, for example, what the access pattern here. For example, if you send a query 1, you're gonna retrieve, for example, let's say tuple 1, tuple 5. If you send a query 2, you're gonna send tuple 1, tuple 10. Right? So the cloud knows exactly what kind of tuple that we, or what are the tuples that we retrieved as a result. Assume that we're gonna use perform, let's say, select style, whatever normal query over the relation data. So in this case, we need to make sure that the cloud even cannot see this candidate pattern. Okay, that's interesting part. It can be one of the idea that you try to use for your class project. Okay, and that's what I worked during my PhD. Okay, so anyway, that's all about the motivation of secure multi-party computations. Okay, so in all cases of secure multi-party computation, we need to have something called protocol. Protocol describe how parties gonna what are supposed to exchange message on the network in general. Okay, so let's have here assume that we have to say A, B, maybe C, D, whatever. They communicate with each other. They interact with each other. So we end up, we have like a protocol, which is going to involve, let's say, the interaction, the computation distributed as, let's say, different parties. So here the protocol is going to manage, exchange all the, measure all the exchange message, perform all the computation in a secure way. Okay? We call this one protocol. Okay, this protocol can be replaced by the trusted third party, right? We can do the same job, that task that you can perform using a protocol using the trusted third party. Okay, good. So the goal was gonna say, okay, instead we have a trusted third party, I can take care of the task, okay, without, you say, compromise the privacy of the entity participating in this computation. Is it easy to have trusted third party? Do you trust me, guys? Of course, yes, yeah. So in this case, if you trust me, then how could you guarantee that I'm gonna give you the right answer, right? What if the case that we have when the participated entity gonna be malicious? Maybe you're gonna provide us to say with the wrong values. What's gonna happen to the result, right? And the most important thing, it's hard to find a party to be fully trusted, right? So in this case, we can replace to do the same task using the secure multi-party computation. Okay, good. Now we need to define the security. There are many protocols, okay, of the secure multi-party computation. Defining the security or prove the security might be not easy job or task with this class, but our goal here, we need at least to understand, the definition, okay? So to define the security for the secure multi-party computation, we can employ a rigorous mathematical framework grounded in the cryptographic principle. The security definition should, you see, include all the realistic attacks that a malicious participant may be or may attempt to stage, ensuring thorough analysis, potential vulnerability, and threats. Okay, so think about here. We do have to say, I know the mouse is moving up and down. Right, looks like it depends on my tone is up. The mouse go up, down. Or my tone gonna be moved down. Okay, please stay here. Okay. There's a malicious user here. One of the participant users, you remotely control my computer, guys. Anyway, so back to the capturing, let's say, the realistic attacks that the malicious participant maybe attempt to stage. We need to make sure that, for example, of course, as we're going to see later, we define the security. Let me jump to this point to get be much clearer here. We need to define, for example, the adversarial model, what the attacker can do. Okay, we need to specify, for example, the capability and the goal of the potential adversaries. Okay, within that protocol that we try to define the security. Okay, here include to say the attacker ability to eavesdrop on the communication, manipulate the inputs, it's the most important thing, or collude with other participants, as you're gonna see here. For example, 3-4 people try to participate in this computation, collide with each other in order to try to defeat the system. Okay, as we're gonna see, we need to formalize the protocol functionality. We need to clearly define, for example, what the intended functionality of the protocol in mathematical terms. Okay, which in this case we need to specify, let's say, the inputs, outputs, the desired properties actually of the computation that we have. We need to identify, for example, what the security. I don't know what's going on. What the security properties. Okay. You need to see, for example, what the protocol should satisfy, for example, confidentiality, or say the privacy inputs, Integrity, for example, it depends. Okay, authenticity depends what you try to achieve. I'm talking about in general, not only in the secure multi-party computation. Okay, then after that you need to define, for example, the security notion. Now we're getting an advanced level. Then after that, how to prove the security theorem and how to consider, the practical consideration. For example, why the definition maybe should be abstract. It should also consider, let's say, practical constraints at the same time the trade-off, such as the computational power or complexity and efficiency. Okay, so if you see here, if you notice here, actually we said the definition should be abstract, right? That means based on the desired functionality, not based on the actual protocol in general. Okay, what does that mean in this case here? If you notice here, we talk about something is called class of protocols. The class of protocols refers to what? A group of protocol or set of protocol that has the similar characteristics, the similar, let's say, objectives. Okay, and these protocols may be address the same common problems. Okay, or provide similar functionality, but they have different implementation, right, strategies, underlying cryptographic techniques. The secure multi-party computation defined as a class of protocols which might include, say, many techniques or approaches, okay, or protocols, which allow, to say, multiple parties to jointly compute a function while keeping their input private, okay? But we have a different ways to achieve that. We're gonna look at some of them, okay? And maybe in this class, at least in this chapter, okay? So these protocols could range from, let's say, simple cryptographic protocols like the Yao-Garbled circuit, which you're gonna look at in a few minutes, to more advanced techniques like fully homomorphic encryption-based protocol, which is the one that we hopefully expect many students are going to try to use this one in order to do their class project. Even adaptive homomorphic encryption, that's fine, but the fully one is the most advanced level. So you see, we have a different class of protocols. Back to the definition of the security should be abstract, which based on the desired functionality. What you try to achieve, you try to use a secure multi-party computation. I'm not going to look at for, let's say, specific protocol, but for the class of protocols in general. Okay, good. Okay, now let's define the functionality. Okay, and we can consider a function just as you say Boolean result or a bit string of inputs and produce a bit string of outputs. Okay, so in this case, for example, assume that we have the user A and B and we wanted to communicate, so we have two entity or two users are going to communicate. So we need to define this function among both of them, okay? So in this case, in order to define the function, we can say here, we have, for example, k input, and we're going to have, for example, k output, right? So assume in our case, k is equal to, so we end up, we have two users or two inputs, and we're going to have two outputs. Maybe someone thinking about how many outputs we have? Two. Why we need to have two outputs? Because we need to have an output that be passed to every single, let's say, party or entity here, right? Okay. Those k output might be the same value or it might be different values. It depends on the function that we need to simulate, okay? Or the one that we need to implement actually in general, okay? So again, each party gonna have a set of bit string as input, and we're gonna receive a set of bit string as output. Since we have k entities participate in this computation, then we end up with have k out. Okay, good. Now we're gonna talk about the ideal and the real model, which is gonna help us in order to define the security in general. Okay, especially in the secure multi-party computations. So the ideal model that we see in this case, we try to achieve the security with the trusted third party. Okay, good. So it's hypothetical scenario because there is no trusted third party does exist. Okay, which you can use in this case. So in this case, assume that we have what? Assume that we have the same scenario. We have, for example, Alice and Bob wanted to communicate or wanted to perform the secure multi-party computation. Okay, assume that we have a trusted third party, which our hypothetical scenario, okay, but it's gonna securely submit their, let's say, input to the trusted party. For example, I'm gonna submit, I have two users, x1 and x2, and the trusted third party is gonna perform the computation. Then after it's gonna be what? It's gonna apply or response with the result, and we can assume that the result is gonna be f1 or F2 or whatever. It might be the same output, or it might be different output. Depends on the function that you try to implement here. Okay? Okay. Here in this case, all the entities are trusted, and we do have a trusted third party. Good. So by just looking to this algorithm, do you think this algorithm, this say scenario, is secure or not? It should be secure, right? Because the trusted third party means trusted, and all the entities be trusted. So everyone send the input x1 and x2. I'm going to, 100% compute, the function. Then I'm gonna apply also respond with the output. It's gonna be the output gonna be correct. Okay, good. Uh, we talk about the secure multi-party competition. We try to have the same scenario. We try to mimic, try to get, something like this. Okay, without having the trusted third party. Okay, and that's what we have. Of course, we use F1 and F2, but it might be the same output, might be the same different output. That's fine. Okay. We claim here, the computation, the ideal model is secure by definition. And this is the reason. All the entities are trusted. The trusted third party is trusted. So you're going to perform the computation and you can produce the result. All of them going to be honest, right? Okay. We don't have to say malicious entity or it's going to produce or give us to say wrong entry or value, which is going to cause, the result going to be inaccurate. Okay. The major goal of the secure multi-party computation is to try to get something like this. That's what same thing we did actually here, right? Good. So here we assume that the protocol is gonna be what? It's secure if it emulates an ideal setting. That's why I said we try to have what? Something like this, okay? Where the party gonna be hands their input to the trusted party who locally compute the desired output and hands them back to the party. So again, try to simulate the exist of the same situation that you have the trusted third party. Okay. In this case, I will draw this one here because I need to use both of them later. So I will use let's say separate both of them. So here the definition of the secure multi-party computation, we have what? We have A and B, and both of them interact with each other as you have a protocol, right? That's the secure multi-party computation. We claim that this protocol can be secure, okay? That means in this case is going to be similar to this case. Or in other words, those or both scenarios are going to be the same. So whatever is going to happen here is going to be similar to what's going to happen here, okay? It might be not clear, but we're going to look at this in details, okay? In the real model, which represent, the actual protocol execution without the trusted third party. Okay, the party relying on what? In the protocol itself in order to achieve the desired security properties. So we claim that this protocol can be secure if we can prove that this protocol is similar to this protocol. Okay, or both cases are the same. Okay, we're gonna do this using what is called, the security by simulation. That means in this case, we try to proving the security of the real world protocol, okay, by comparing the adversary view, as we're gonna see later. We're gonna be assume that gonna be like all the messages received by each party this view, okay, by comparing the adversary view here in the real model with the actual protocol execution. It's gonna be similar to the view here in the ideal model with the trusted party, so you can easily assess the protocol security. Okay, we're gonna have example later in details. So that's what they've said here. Okay, so the real and ideal model paradigm for the defined security, very important paradigm. Okay, it has two parts. We have ideal model and the real model. The ideal model doesn't exist. It's the hypothetical scenarios where we have a trusted third party. We're gonna get the input and perform the computation, produce a result, and share the result with all the parties. The real model, the actual, let's say, protocol execution, as we said here, without the trusted third party, okay, where the party can be communicate or rely on the protocol itself in order to perform the computes, the function, and to say share the result, okay? The security protocol can be checked by comparing what an adversary can do in the real protocol execution to what it can do in an ideal scenario. We say in this case can be simulation, right? So a protocol is secure if any adversary in the real model can do no more harm than if it was involved in ideal model. What does that mean in this case? We can say the secure protocol ensures that adversary cannot distinguish between the real and the ideal model execution. And that's what I summarize here. Okay, so in this case, so in other words, the adversary observation and interactions in both scenarios should be statistically indistinguishable. Okay, so I won't talk about this one in details. We'll talk about the adversary model and the malicious behavior. Okay, so this, I mean, the takeaway of the slide. The real ideal model paradigm provides a strong foundation for analyzing protocol security. If an adversary can achieve certain outcome in the real world, that couldn't be in the ideal scenario, so it indicates that we have a security issues or flaw, or let's say weakness of the system. This should have what indistinguishable. So you cannot, the attacker cannot distinguish whether it's gonna communicate with you, say, real world or the ideal world. That's the thing that you try to simulate. Actually, this is what we've said here. So this summarizes what we have said in the last slide. Okay. So now we're going to talk about the adversary model. We need to define how the attacker behaves. Okay. If I give you two entities communicate with each other, Alice and Bob, which one is going to be the adversary? It might be one of them. It might be both of them, right? So here, if all the entities are honest, then in this case, there is no need to have a secure multi-party computation, right? Because you trust each other. No one is going to be maliciously behaved. Then in this case, we don't have a secure multi-party computation to perform the task that we try to achieve. Okay, good. So now we have, I mean, the semi-honest. We call this one the passive or honest but curious. Let's define what do you mean by this definition. So when you talk about the semi-honest, that means this, the attacker in this situation is act as the passive attack. It's not gonna interfere with normal interaction. It's not gonna lie. It's not gonna, for example, leave, the computation in the middle. It's not gonna, for example, try to cheat. But what they try to do here, based on the output that I have, based on the message that exchange, I will try to do my best in order to what? In order to get the private information associated with the other party. Right? So, but still passive attacks. Okay, I'm not gonna come up with a fake message. I'm not gonna cheat. I'm not gonna lie about my input and output. Okay, good. Let me break down what you mean by the semi-honest. Okay, so in this case, we have Alice and Bob. Okay, either one of them, either both of them. Okay, when I say they are honest, that means in this case they are not gonna lie. They're gonna provide me with the actual data, right? Where they say, give me the value of A. Your private input. A is gonna give us the private input. Of course, should have somehow secure communication with, to exchange this private information. But you are not gonna lie about your data. Okay, good. What else? So let's say, let me write this one. Don't fake data. Can I say this one? Fake data. Okay. No lying. Good. This honest. But not honest 100%. Why? Because in this case, you try to do what? You try to get your private input. That's why I've said, it's going to try to violate the privacy. Okay? Good. Malicious, it's clear, right? The ones who try to do all they can in order to cheat, lie, stop in the middle of the exchange the message. They're not gonna finish the protocol, and they try at the same time to get your private input. That's the goal here. Okay, so what we're gonna do right now, we're gonna focus on the semi-honest. Okay, then after that we talk about the malicious. Okay, and also two-party protocols. Good. Remember the models that we have, and now is there a way in order to prove whether they are, for example, the same or not, whether they are too close or not. So we're going to look at the correctness and you see the security, which the main major property of secure multi-party competition. We have more, okay? Now, how to prove the two models that we covered in a few minutes are close or similar, right? So we're going to look at two security properties, or two properties that secure multi-party competition should ensure the correctness and the security. we're gonna see the correctness is easy to achieve, it's to prove. The problem with the security, it's not, I mean, straightforward. But we're gonna show you a way how to perform that. Okay. So when you talk about the correctness, there's means in this case, if you look at the scenario that we have here for the trusted third party, when each party can be sent their private information, then the trusted third party can perform the computation, then compute the function, then share the result. Everything's gonna be fine, and the outcome gonna be the right answer, definitely, right? And here for the A and B, since both of them is gonna be honest, they are not gonna cheat about their value, and this protocol is gonna manage in order to compute the correct answer. So the result here is gonna be similar to the result here in this case. Okay, good. So in other words, all the honest participants are gonna be what? You're gonna receive the correct result of evaluating function f, because the transfer part is gonna be compute the value of f correctly, and the same thing is gonna be for the protocol. So it's easy to prove that both of them achieve the correctness. For the security, remember, I'm talking about the semi-honest, right? I'm not going to talk about the malicious adversary. For the security here, we need to make sure that all the corrupted, participants, okay, or the parties should learn no more from the protocol than what they would learn in the ideal model. What we can learn from the ideal model, actually, we have two things. I mean, of course, your input and the output. This is the only thing that we can learn. For the let me write this one here. Here, what kind of information you got to learn? For example, for A, this is input and this is output, right? For B here, it's gonna be input x2 and the output f1, right? And here we can simulate the same situation. If A, for example, input x1 and x2 here, and the function f, this is gonna be produce the result of the f1. So for A, it's gonna be the input x1 and the output, say we call this one f1, okay? And here for B, it's gonna be the input x2 and the output gonna be f2. So right now we can see, okay, whatever I have here, it's gonna be similar to whatever I have here, right? Nothing else. But since we have a protocol, we're gonna exchange more messages, okay? So there's a chance that we have what? We're gonna have, for example, maybe more data computation exchange message, which produces some extra maybe information gonna be here. But we've tried to prove here, whatever the view that we have, which in this case, as I mentioned before, is defined as all the messages received by each party. So the view of A here, it's gonna be similar to the view of A here in the ideal model. So the real model is gonna be similar to the ideal model. Or I can simulate the same view here. So in this case, even with this extra piece of information, so I can, assess whether my protocol is gonna be secure or not. So again, whatever you're gonna achieve here can be simulated here. Oh, so in this case, this trusted third party, okay? Only the input can be known by the trusted third party, and the only information you can learn here, the input and your output. Your input and the output that you received from the trusted third party. All right, good. So here we try to do what? We need to have to say a way to prove that these additional messages do not reveal any extra information or knowledge. Okay, good. So again, this approach can be done using the simulation, which is going to be talk about the next slide.